Hello, my name is Kengo Nakajima, University of Tokyo. The title of my talk is Integration of Simulation plus Data plus Learning for Innovative Scientific Computing by h3-Open-BDEC on Wisteria BDEC-01. First, I'll make an overview of the Wisteria BDEC-01 system with A64FX, which started its operation on May 14, 2021 at the Information Technology Center, the University of Tokyo. Then I'll talk about h3-Open-BDEC, which is an innovative software platform for scientific computing in the exascale era. This slide overviews the three systems of our supercomputer center at the end of March 2021. We have more than 2,600 users, and more than 55% of them are from outside of the University of Tokyo. The oldest one is ReadBush by HPE, which consists of Intel Xeon Broadwell and NVIDIA Tesla P100 Pascal GPU. This is our first GPU cluster. Ocre-Sparks by Fujitsu is with more than 8200 of Intel Xeon Phi many-core CPUs. This is operated by JCHPC, which is a joint work by University of Tsukuba and University of Tokyo. Total peak performance is 25 petaflops, and it is the 22nd in the top 500 list, November 2020. The third system is OakBridge CX by Fujitsu. It has 1,300 nodes of Intel Cascade Lake. Total peak performance is 6.61 petaflops, and it is ranked 69th in the world. Two pie charts show research areas of ReadBush based on CPU hours. Left chart shows usage of ReadBush U subsystem equipped with only CPUs. Computational sciences, such as simulations in engineering, earth and space science, and material science, are the typical areas of usage of our supercomputer systems in recent 55 years. On the contrast, workloads on GPU cluster are very different. Large portions are occupied by information science related to artificial intelligence and bioinformatics, such as genome analysis and medical image recognition by machine learning. Next page shows research area of Ocre-Sparks and OakBridge CX. These are mainly used for computational science, but there are certain amount of usage in bioinformatics. Our systems are used in projects for fighting against COVID-19, supported by Japanese government. In 2020, 14 projects were conducted, and 6 of them used our systems. These simulations for splash diffusion are done by my colleague Professor Tsubokura from Kobe University and Riken. Although his results on Fugaku supercomputer are widely known, he also used our supercomputer system, OakBridge CX. Our systems are used for global atmosphere-ocean coupled simulations on climate and weather. Solid Earth and earthquake simulations, simulations of geologic CO2 storage. This slide overviews the real-time prediction of severe rainstorm. This was originally planned for 2020 Olympic and Paralympic Games in Tokyo and was done in September 2020. Large-scale simulations, observation by satellite and phase array radar were combined with data assimilation for a real-time forecast of severe thunderstorm. In this study, we propose an innovative method for computational science towards the exascale era and Society 5.0 by integration of simulation plus data plus learning, S plus D plus L, where ideas of data science and machine learning are introduced to computational science. Society 5.0 is proposed by Japanese government, aiming super smart and human-centered society by digital innovation such as IoT, big data, AI, etc., and integration of cyberspace and physical space. It follows hunting, agriculture, industry, and information from Society 1.0 to 4.0. Supercomputing is changing now. As I mentioned in the previous slides, we have new types of workloads related to big data analytics, AI, and machine learning, in addition to CSE for simulations. Integration and convergence of S plus D plus L is important towards Society 5.0. We have been developing a platform for integration of S plus D plus L since 2015. Name of the project is BDEC, Big Data and Extreme Computing. BDEC is focusing on simulations, Our approach is based on AI for HPC or sophisticated simulations. We have been operating 3 supercomputer systems and now introducing the BDEC system as a platform for integration of S plus D plus L. Name of the system is Wisteria BDEC-01 with a 33.1 petaflops peak performance. This slide shows the schedule for procurement of supercomputer systems in the University of Tokyo. We are now in the mid of fiscal year of 2021, and Wisteria BDEC-01 has started its operation in May 2021. Wisteria BDEC-01 is the first BDEC system, big data and extreme computing, which is the platform for S plus D plus L. Peak performance is 33.1 petaflops and aggregated memory bandwidth is 8.38 petabytes per second. The system is constructed by Fujitsu. Operation started on May 14th this year, and it is a hierarchical, hybrid, and heterogeneous system. Simulation nodes for HPC, Odyssey, with more than 25 petaflops is based on Fujitsu's Prime HPC FX1000 with A64FX with high bandwidth memory. This part has the same architecture as that of the Fugaku supercomputer. Data and learning nodes, Aquarius, are GPU cluster consisting of Intel Ice Lake and NVIDIA A100 Tensor Core GPUs, with 7.2 petaflops for data analytics, AI, and machine learning workloads. Some of data and learning nodes are directly connected to external resources, such as servers, storage systems, and sensor networks. This table shows the rankings of several benchmarks, such as the Top 500, Green 500, HPCG, Graph 500, and HPL AI, which was presented at ISC 2021. So currently, Odyssey and Aquarius are separately operated. Wisteria is named after the legend of the Princess Wisteria at Lake Teganuma in Kashiwa City, where the building for the system locates. Each of Odyssey and Aquarius is corresponding to the call sign of the command module and that of lunar module of the Apollo 13. We hope that Wisteria BDEC-01 saved the Earth as Odyssey and Aquarius supported crew of the Apollo 13 to come back to the Earth safely. This is how we utilize the Wisteria BDEC-01 system for integration of simulation plus data plus learning. Models and parameters for simulations are optimized by data analytics and machine learning. h3-Open-BDEC is an innovative software platform for integration of S plus D plus L on the BDEC system. It is a 5-year project supported by Japanese government since 2019. PI is Kengo Nakajima, and total budget is $1.4 million for 5 years. Collaborators are specialists of the computer science, high-performance computing, HPC, computational science, numerical algorithms, data science, and machine learning. h3-Open-BDEC is the innovative software platform for integration of S plus D plus L on BDEC system. We have 2 significant innovations in h3-Open-BDEC. One is innovative method for numerical analysis with high performance, high reliability, and power saving, based on the new principles of computing by adaptive precision, accuracy verification, and automatic tuning. Mostly, scientific computing has been conducted using FP64 double precision. Sometimes problems can be solved by FP32 or lower precision. Computing with lower precision generally saves computation time, energy, and memory. Approximate computing is originally the idea for image recognition, etc., where accuracy is not necessarily required. It is also applied to numerical computations. Computations by lower precisions and by mixed precisions from half to quad precisions are widely used in various types of scientific applications, but such computations may provide results with less accuracy. P3D is the target application in the present work, which solves steady-state heat conduction problems by finite volume method, FVM, based on operations of 7-point stencil. Distribution of thermal conductivity lambda is heterogeneous. One layer with different material property, lambda 2, is inserted. Ratio of lambda 1 over lambda 2 is proportional to the condition number of the derived coefficient matrix. The derived coefficient matrix is sparse and symmetric positive definite, SPD. Linear equations are solved by ICCG, conjugate gradient iterative solver with incomplete Cholesky precondition. The code is written in Fortran 90 and OpenMP, and CM-RCM reordering is applied for thread parallelization. P3D supports FP64 double precision, FP32 single precision, and FP16 half precision, while FP16 can be only applied to preconditioning. Moreover, it supports various types of matrix storage formats such as CRS, ELL, Celsius sigma, etc., while CRS, ELL, and optimized ELL are applied in the present work. Performance was evaluated on a single node of OFP with Intel Xeon Phi, OVCX with Intel Xeon Cascade Lake, and OL7 FX700 with Fujitsu A64FX. Next slide shows performance of ICCG solver for three types of matrix storage: CRS, ELL, and optimized ELL, for both of medium and large-sized problems. FX700 green bar is rather slower than others with CRS, but much faster with optimized ELL, especially for larger problems. This slide shows that we need certain optimizations for extracting performance of A64FX. Another important feature is that we can easily implement FP16 half-precision operations on A64FX using Fujitsu's compiler. Here, we evaluated the robustness of the ICCG solvers of using mixed precision computing, including FP16. In double half DH and single half SH, preconditioning part is implemented using FP16. Next slide shows implementations of word substitution procedure in ICCG. Difference between double single and double half is difference of precision of coefficient matrix, FP32 or FP16. Next slide shows relative error compared to double-double implementation at the bottom point of the target geometry. Error increased as lambda 1 lambda 2 ratio increases for single-single and single half cases. On the contrast, error stays zero for double single and double half, while they do not converge if lambda 1 lambda 2 ratio is equal to 1 million. This slide shows number of iterations normalized by iteration for double-double cases. Iterations for double single and double half are equal to those of double-double if lambda 1 lambda 2 ratio is smaller than 100,000. Another innovation is hierarchical data-driven approach, HDDA, based on machine learning for integration of S plus D plus L, AI for HPC. Because real-world scientific simulations are generally nonlinear, we need to do huge number of parameter studies. Therefore, reduction of cases is very critical. For example, mid-range weather prediction is done by 50 to 100 ensemble cases. It is known that we need 1,000 cases for accurate solution. If the optimum parameters can be selected by machine learning, 50 to 100 or fewer cases may be enough for accurate solution. Data-driven approach, DDA, is a widely known method. Techniques of AI and machine learning is introduced for predicting the results of simulations with different parameters. DDA generally requires order of 1,000 to 10,000 runs for generation of training data. We are proposing HDDA, hierarchical DDA, in this project. Simplified models with coarser meshes, but preserving original features of physics for efficient trainings are constructed automatically by machine learning, using various types of methods such as feature detection, adaptive mesh refinement, model order reduction, uncertainty quantification, and sparse modeling. This slide shows the result of preliminary works by my colleague Professor Shimokawabe. This is for prediction of a transient CFD simulation by machine learning and convolutional neural network. The current result shows good agreement between 2D lattice-Boltzmann simulation and CNN predictions. One of possible applications for integration of S plus D plus L using h3-Open-BDEC on Wisteria BDEC-01 is simulation with data assimilation. We are working together with AORI, University of Tokyo, RIKEN RCCS, and National Institute of Environmental Studies in atmosphere-ocean coupling for weather and climate simulations. Moreover, we also started collaborations with Earthquake Research Institute, University of Tokyo, for earthquake simulations with real-time data assimilations. We can extend this idea to real-time disaster simulations such as flood and tsunami. Furthermore, we can apply integration of S plus D plus L to existing simulation codes, such as OpenFOAM. JDXNet is a seismic observation data exchange and distribution network in Japan, and it distributes the seismic observation data of the 9 national universities, JMA, NIED, JAMSTEC, AIST, etc. This slide overviews 3D earthquake simulation with real-time data observation and assimilation. We utilize real-time observation data, including satellite data of JDXNet through SciNet. This is an example of 3D earthquake simulation with real-time data observation and assimilation. It starts from combined simulation with real-time data assimilation and switches to pure simulation. One of the purposes of this application is safer evacuation in case of emergency. Another one is improvement of underground model by machine learning, which will be done under normal operations. We are now doing preliminary studies using our Oakbridge CX, OBCX system. OBCX has more than 1,300 of nodes of Intel Cascade Lake scalable processors. 128 of these nodes are equipped with fast SSDs. Furthermore, 16 of these 128 nodes are directly connected to external resources through SciNet. We are using one of these nodes for getting real-time observation data from JDXNet. We are going to install the application to Wisteria BDEC-01 after May 2021. On the Wisteria BDEC-01, Aquarius is doing filtering, machine learning, and visualization, while Odyssey works for data assimilation and simulations. Because the Wisteria BDEC-01 is heterogeneous, a single MPI job of Odyssey and Aquarius is impossible. Actually, they are connected through InfiniBand EDR with 2 terabytes per second. We are developing a communication procedure with the h3-Open-BDEC weight I/O library for inter-process communication with MPI-like interface, and h3-Open-Util-MP multi-physics coupler. Generally, multi-physics coupler, such as PP-OpenMath-MP, is doing weak coupling of multiple applications, but our new coupler, h3-Open-Util-MP, has more sophisticated capabilities. One innovative idea is to couple computational science simulations in Fortran and AI workload written in Python using Fortran Python adapter. We are developing a new coupler which combines Odyssey for simulations and Aquarius for AI machine learning through InfiniBand EDR. Current version of the coupler is based on a single MPI job environment. Direct communication is conducted between Odyssey and Aquarius through InfiniBand EDR by h3-Open-BDEC weight I/O, which provides MPI-like interface. This slide provides a schedule for public use of these libraries. MPI version of Simulation AI Coupler is available this October. InfiniBand version for heterogeneous environment is open for public between January and April next year. This is a summary. By integration of S plus D plus L using h3-Open-BDEC, total energy consumption or total computation time for simulations will be 10% of that by the conventional method for simulations with parameter studies. h3-Open-BDEC is the first innovative software platform for integration of S plus D plus L on exascale systems where computational scientists can achieve such integrations without support by other experts in data analytics and AI machine learning. Source codes and documents in English are open to the public for various kinds of computational environments. Thank you very much for your attention.